welcome you all in today's lecture of the mechatronics course. Today we are going to discuss the actuation systems. You see, in a mechatronic system, the actuation system has got a very pivotal role to play. The actuation signals are obtained from the microprocessor, and these signals are given to the actuator to perform a specific type of task. Okay. So, in a control system or in a mechatronic system, as I said, actuation system has got very important tasks to do, and today we are going to see one of the very important type of actuator, that is the electrical actuators. Okay. Why electrical actuators are important? Because these actuators are very easy to control, okay, as compared to the say hydraulic or pneumatic one. Okay. So, we will be today looking at through two of the lectures. I will be talking about the electrical actuation system 1 and electrical actuation system 2 today. So, switching devices, as I said, in a mechatronic system we require the control signals, okay, and these control signals may be switching on and off to some electrical devices. So, what could be these switching devices? Okay. So, these switching devices could be, say, if it is a mechanical device, then it could be simple relay, and if it is a solid state device, then it could be diodes and transistors. So, use of diode and transistors or their basic principle I have already discussed with you in our initial lectures. The solenoid type of devices are used in hydraulic and pneumatic systems, as I have talked about them in my lecture on the hydraulic and pneumatic system, where we have seen that the solenoid is used to actuate the valves. Okay. So, in these solenoid type devices, basically current through a solenoid is used to actuate a soft iron core. Okay. So, the actuating device could be solenoid type device, or it could be a drive system, and in drive system under electrical actuation we are using the DC and AC motors. Okay. And aim could be to select a motor for a specific type of mechatronic application. So, towards the end of my second lecture in electrical actuation, I will be also talking about how do we select a particular type of motor for a mechatronic application. Let us first begin with electromagnetic principles. Okay. Before I go to the different type of actuating devices, let us look at some of the fundamental things. Okay. So, Lorentz law is one of the basic fundamental law, or which basic provides the principle for the electromagnetic actuation. Okay. So, the law says that when a current conductor is moved in a magnetic field, a force is produced in a direction perpendicular to the current and the magnetic field. Okay. So, as you can see in this figure, okay, it is basically something like this. You have your thumb, and you have this finger and the middle finger. Okay. So, if this is the direction for the current, okay, and this is the direction for say the magnetic field, then this is going to be the direction for the force. Okay. So, the Lorentz law in a vector form is represented by say F is equal to I cross V, where cross is the vector cross product. Okay. Here F is the force vector expressed per unit length of the conductor, and I is the current vector, and B is the magnetic field vector. Okay. And this relationship is given by the right hand analogy as I showed you. Now, if we talk about the field intensification within a coil, okay, when a current is passing through a conductor, you see the magnetic flux through a coil is proportional to the current which is passing through the conductor through the coil and the number of turns in it. Okay. And if we replace this proportionality sign with a equal to sign, I put a constant k. Okay. And this k is function of permeability of material within the coil. Okay. And you see the permeability is a property or characteristic how easily magnetic flux can penetrate the material. And to give you some idea about the permeability, say iron permeability is around 100 times that of the air permeability. Okay. And the cores are laminated basically to reduce the eddy current losses. Okay. That is there. Now, let us look at the first device, that is the relays. Okay. It is an example of electromagnetic switch. Okay. And it is used in application to turn on or off circuit by a say low power signal. Okay. And when there is a current through the solenoid of the relay, basically a magnetic field is produced, and which attracts the iron armature. Okay. And this may move the lever, and and this moves the lever. So, what happens is basically the it closes the normally open switch contact, and it opens the normally closed switch contact. Let me explain this to you further through this schematic figure. So, you see that this figure illustrates the normally open circuit. Okay. So, you can see that in this circuit there is a spring basically put into here, and this spring pulls this lever, and because of this there is always this contact is open. Okay. This contact is open, and now when the current is supplied to this solenoid, okay, a magnetic field is produced, and that because of that this gets attracted over here. Okay. Because of this this lever gets attracted over here, and this contact closes basically. Okay. So, this is with the normally open switch, and if we look at the normally closed switch here. So, in case of normally closed switch, actually this is the normal position, you can see. Say if this is the spring which is attached to the lever. So, this always pulls towards this end. So, this contact is normally closed. Now, when you pass the current through this solenoid, then what happens, this gets magnetized, and in turn it attracts this lever. Okay. There being a magnet over here. So, it attracts this, and this way this circuit opens. So, let us look at how does the solenoid work. Okay. So, the solenoid which we have discussed or explained you over here, okay, its working principle is something basically like this. There is a movable armature core, as you can see here, there is a coil, and there is a stationary iron core over here. Okay. Now, what happens when you supply the current through the coil, then a magnetic field is produced, and this movable iron core, armature core, gets attracted. Okay. So, there is a motion in this movable armature core. Okay. And once naturally and when it gets attracted, it presses this compresses this two springs, and when the current supply is switched off, then these two springs actually expands, and this goes back to the movable armature core goes back to its original position. Okay. And this is how a push pull type solenoid is commercially available in the market. Okay. Now, coming to the electrical motors. Electrical motors are used in position control systems, used in the position control systems or in the speed control systems. Okay. And these motors could be classified as DC motor and AC motors. Okay. And the DC motors are mostly used in the modern control systems because of these motors are easy to control. So, the basic principle which we have seen, the force here you see that if there is a current carrying conductor placed in a magnetic field and the current through the conductor is I, okay, and the field is perpendicular to the current direction, okay, then you are going to have a force produced F, and this F is given by BIL as per the Lorentz law. Okay. And when this conductor moves in a magnetic field, then an EMF is induced across it. I will be talking about a little more about this, and this induced EMF is basically given by E is equal to minus d phi by dt, where phi is the flux linkaged basically, okay, through the conductor. Okay. And this is you know the as per the Faraday's law, and there is a negative sign here basically, and this negative sign indicates that EMF is in this induced EMF is in such a direction as to oppose the charge producing it. Okay. And this is popularly known as the Lenz law. You must have studied in your say intermediate classes. Okay. And this direction of induced EMF is such that it produces the current which sets up a magnetic field, and that magnetic field tends to neutralize the change in the magnetic flux linked by the coil, and which was responsible for that particular EMF. Okay. And that is why we also call it as the back EMF. Okay. So, that is there. Now, after looking at this principle, let us see the DC motor, and in DC motor as you see that we have a magnetic field is being produced by the magnet, and there is a conduct carrying coil which is being placed over here. Okay. So, that is there. So, a loop of wire which is free to rotate in the field of permanent magnet is there, and when a current is passed through the coil, a force acts on the right angle to the field. Okay. And you see that for this rotation to continue, basically, okay, for this rotation to continue, we need to change the current direction. Okay. So, for example, here you see that in this conductor, okay, say this is your I, this is your B, so this is your F. Okay. And whereas in this conductor current is in this direction, in this side the current is in the reverse direction. Okay. So, you have the force F being acting in this direction, and this force basically forms a couple, and it tries to rotate this about this axis. Okay. And you see that for this rotation to continue, when this reaches at this position, there has to be some switching mechanism to reverse the direction of current, so that it keep on rotating. So, in the conventional DC motors, coils of wire are mounted in the slots. Basically, as you can see, these are the slots where the coils of wire are mounted on a cylinder of magnetic material, which we call as the armature. Okay. And this armature is mounted in the magnetic field produced by the field coil. So, instead of the permanent magnet here, we could have the field coil, okay, and which generates the magnetic field. Okay. So, that is there, and the ends of the armature conductor here, armature coils, are connected to adjacent segment of a segment ring, segmented ring, which we call it as a commutator, with electrical contact made to the segments through carbon contact, usually called as bushes. So, that is done for changing the sign of the current in the conductor. Okay. So, as the armature rotates, the commutator reverses the current in each coil as it moves between the field poles. Okay. And this is necessary if the forces acting on the coil are to remain acting in the same direction, and if the rotation has to be continue. Okay. And the direction of rotation can be reversed either by reversing the armature current or the field current in this case. Now, let us look at the permanent magnet DC motor. Okay. The permanent magnet DC motor, here the motor which that is the armature which is placed in a field produced by the permanent magnet. Okay. So, let a permanent DC motor, the permanent magnet giving a constant flux density, constant value of the flux density, and you see that the here this is that constant value of the flux density B, and if we supply current I through this one, okay, then the force acting on the conductor, right angle to conductor, is going to be BIL. Okay. And if we have n such conductors, this force is going to be n times of that, and the force results in a torque T about the coil axis. So, this force and this force basically form, as I said, they form a couple, and this its moment is given by the force into the distance between these forces. So, FB, where B is the width of the coil. Okay. So, this torque is FB, and this is times NBIL times B. Okay. Now, here what I do is that I separate this I here. So, I have this constant. What is the constant over here? See, this n is the number of turn, it is constant. B is the field strength. We have already assumed that the permanent magnet is giving the constant value of flux density. So, you have the constant field strength. L is the length of the conductor. Okay. So, this is constant, and this B this value is also constant, and I rename this constant as say kT, and this kT is popularly called as the torque constant of the motor. Okay. So, this is there, and since armature is rotating in a magnetic field, electromagnetic induction will occur, and the back EMF will be induced, which I have talked in my previous slides. Okay. And this induced back EMF is proportional to rate at which the flux is linked by the coil, flux linked by the coil changes. Okay. And for a constant magnetic field, the back EMF is proportional to the angular velocity of the rotation. Okay. And if I replace that proportionality sign, I can write this back EMF is equal to kV into omega. Okay. And this kV is back EMF constant. Okay. And this is how a commercially available the permanent magnet DC motor looks like. This is a product of Sivu Industrial Systems company limited. Now, let us look at the equivalent circuit of the DC motor which I talked to you. Okay. Now, armature coil being represented by a resistor and an inductor in series. So, to represent the motor, to represent the armature, armature coil has got a certain resistance and it has got a certain inductance. Okay. So, I can represent this resistance and inductance in series for this. You have a motor here, this VB is the back EMF and this V is the voltage supplied. Okay. Now, to simplify the analysis, let us assume that this L is negligible. Okay. So, if this L is negligible, then what are the voltages here? We have V minus VB is the net volt which is driving this circuit. So, I can find out the current as V minus VB by R, and this is going to be the current. Okay. So, this I am now replacing this VB by kV omega. So, this is V minus kV omega by R. So, this is my current. So, the torque I can write the torque constant of the motor kT into the current I. Okay. So, now I substitute for this I over here. So, I have kT by R V minus kV omega. Alright. Now, you see here what happens during starting, when the motor starts, then at the time initially omega is 0. So, if I keep this omega 0 in this equation, then what happens, my torque is proportional to V. Okay. And when there is no load, if there is no load, that is if I keep the torque is equal to 0 in this equation, then what happens, I can see that my omega is going to be proportional to the voltage. Okay. So, let us look at how these variations looks like. So, you see that our equation for torque and current is T is equal to kT times I. So, as the current increases, the torque increases basically. So, you can see the linear relationship over here. And if I plot the torque versus angular speed, so that I can do using this equation, okay, and you see that as the voltage increases basically it's keep on shifting, there is a parallel shift in this characteristic curve, and you see that when we have angular speed 0, okay, when omega is 0, we have the maximum torque, okay, which we also called as the starting torque, okay, and at when there is no load, that is when torque requirement is 0, we have the maximum angular speed. Okay. So, this is the characteristic for corresponding to voltage V1, corresponding to voltage V2, and if V2 is greater than V1, naturally then here its torque is going to be more. Next, let us take up the DC motor with the field coils. Okay. So, DC motor with field coils, as you see that our rotor is placed basically in a magnetic field produced by the field coils. Okay. So, this is the case actually, the one which I was talking to you. Okay. So, you have the field coils over here, okay, and here is your armature. Okay. Now, the thing is that how these field coils are connected with the help of armature to the armature. Based on that, we can have the different type of classification, and we can have the different type of characteristic of the motor. Okay. So, suppose I have the armature here represented by its resistance and inductance, and your field coil, okay, again represented by its resistance and inductance. Now, if they are connected in series, basically what we get is as the series wound DC motor. Okay. So, that is there VB is the back EMF here. Okay. So, in the series wound DC motor, basically the armature and field coils are in series. Okay. So, you can see that the armature coil and these are the field coils, these are in series. Okay. Motor exert higher starting torque and has greater no load speed in this case of, in the case of DC motor with series wound field coil. And now, here you see that since armature and field coil, they are in series, if you reverse the polarity of the supply, you are not going to have to any effect on the direction of rotation of the motor, since both are connected in the series, because you are going to have change in the current direction in the both. Okay. And in this case, the torque and current characteristic is going to be like this, and the torque and speed characteristic in case of the series wound motor is like this, and this value, the starting torque, as I said, motor exerts higher starting torque. Now, let us look at the shunt wound. In case of shunt wound, what happens, this armature coil, okay, and the field coil, they are in parallel, basically they are shunted. Okay. So, and say this is the motor, VB is the back EMF which is being generated. So, here the armature and field coils, they are in parallel, and it provides lower starting torque, lower no load speed, and good speed regulation. Okay. So, this starting torque is lower, this no load speed, this is also lower, and you can see that this portion is almost a straight line, Okay, it has good speed regulation. It could maintain a constant speed, as you can see. Okay, so the constant speed regulation of load is possible with the help of the shunt wound motor. Okay, and to reverse the direction of rotation, either the armature or field supply can be reversed, and we could change the direction of rotation of the motor. This is the characteristic for the torque and current. As current increases, the torque is going to increase. Then we have the case of compound wound. Okay, so compound wound, a field winding, part of the field winding is in series with the armature winding, and the part is in parallel with the your armature winding. Okay, so this type of one is called the compound wound, and this gives the combined feature, that is the higher starting torque and the better speed regulation. So, the best of both series wound and shunt wound you get in this case of the compound wound motor. Okay, so this is the torque speed characteristic which looks like, and this is the current and torque characteristic which the motor has. Then we could have a situation where we could have the separately excited motor. Okay, so this is basically a special case of the shunt wound motor, where we have the field coil, okay, which is not having the contact with the armature coil, and they are separately excited. Okay, so it's a we can deal with this type of condition as a special case of the shunt wound motor. Now, if I look at the torque and angular speed of characteristic of these three motors, then this is what we see behavior for the series wound, this is the behavior for the compound wound, and this is the behavior for the shunt wound. Okay, so you can see that the compound wound characteristic is in between that of the series and shunt wound motors. Next, let us look at the permanent magnet DC motor characteristic. Okay, so if I talk in terms of starting torque, say Ts, okay, subscript S I am using to indicate its starting, and no load speed, and you know the no load speed is going to be the maximum speed. Okay, so I am representing the no load speed as the omega max. All right. Now, you see at omega is equal to omega max, when there is no load, that torque requirement is naturally going to be 0, and at omega is equal to 0, that is when the motor is not starting, okay, or about to start, that time this torque is going to be equal to the stall torque. Okay, so this is basically what we had. This is basically Ts, and this is actually the omega max. Okay. Now, you see I can represent this relationship with the help of a single equation, that is T is equal to Ts 1 by 1 minus omega by omega max. Okay. So, you see if I put omega is equal to omega max in this equation, what I am going to get is this factor will be 1. So, this is 0. So, I will be having T is equal to 0. So, the first part I will be getting, and if I am putting omega is equal to 0 in this one, then my torque is going to be Ts. So, I am getting the second part. Okay. So, this way this equation generalizes or depict the relationship for both this part. Now, the torque requirement or the torque of generated by this permanent magnet DC motor is given by the torque constant into current, and you see the current I can write V minus kV omega by R, where that is basically V minus, this is VB, actually the back EMF part. So, V minus VB by R, this one is there, and then I can expand this is KTV by R minus KT KV omega by R. Okay. And so, you see, if we put omega is equal to 0 in this torque equation, then what I get T, this is basically Ts at omega is equal to 0, and this is what I get as Kt into V by R. Okay. And also I can get the maximum value of omega if I put T is equal to 0 in this equation. Okay. Then I could get the maximum value of omega over here, that is Ts into R by Kv Kt. Okay. So, that I can get from over here. So, basically we can talk about what is going to be my power delivered. Okay. So, that power is actually T into omega, and T I am writing as Ts 1 minus omega by omega max times omega. Now, what I can do is that for maximum torque I can differentiate this expression with respect to omega. Okay. So, that my expression was P is equal to T into omega. Okay. The previous one, this one. So, this is omega Ts 1 minus omega by omega max. Now, if I differentiate this, then I can take what I get over here is Ts minus 2 omega by omega max, and if I equate this 0, then what I will be getting is omega is equal to omega max by 2. Okay. So, for maximum power, the speed of the motor has to be equal to the half of the maximum speed. I can also get the stall current that will be when the motor is not running, that is the back EMF is going to be equal to 0. So, stall current is going to be V in by R similar, okay, because your Is is basically V minus Vb by R. So, if this is 0, you have V in, this is input voltage by R. So, the speed current curve for a DC motor is going to look like this, the T is equal to Kt times I, Kt by R, V minus Kv omega. So, from here I can get Tr by Kt is V minus Kv omega, or your Kv omega is going to be equal to V, I can take this side is equal to Tr by Kt, or V minus this is Ir. Okay. That is T, I can put Kt times I, this T is basically torque constant into current. So, Kt times I into R, Kt get cancelled. So, I get V minus IR. Okay. So, from here I can get this value of omega is equal to V by Kv minus Ri by Kv. So, and when the dynamics of the motor and its load both is considered, then the generated motor torque will be given by this polar moment of inertia of armature plus polar moment of inertia of the load into d omega by dt plus frictional torque plus the load torque. Okay. This is there, and for the steady state condition you see that this portion is going to be 0 because your omega is going to be constant. So, this is equal to Tf plus Tl. And also the V in is basically this is L di by dt plus Ri plus Kv omega, because you see that we have modeled the armature as resistor and inductor here. So, this is basically your Vb, okay, and you have here V in actually, this is your R, this is your L. So, if you apply Kirchhoff's law over here, you will be getting this equation, okay. And again for steady state, this term is going to be 0. So, you have Ri plus kV omega, okay. So, if I could plot the power and the torque versus angular speed, so you see that this power is going to come maximum at half of the maximum speed over here, and this is my torque speed characteristic. So, this is the torque which I have been talking to you, that is the stall torque, and this is the no load speed which I say as the maximum speed. Now, the question is that how do we control these DC motors basically, okay. So, the control of these DC motors actually depends on the current through the armature coil, okay. And with a field coil motor, the speed can be changed by either varying the armature current or the field current, generally with the armature current. So, if it is a permanent magnet motor, then you have to do with the current through the armature, and if it is a field winding, then you can do with either the field current or with the armature current, you can try to control it, okay. So, thus the speed control is possible by controlling the voltage which is applied to the armature, okay. And since fixed voltage supplies are often used, a variable voltage is obtained with the help of a electronic circuit or switch, and this forms the basic principle of what we call it as the PWM or the pulse width modulation. So, you have a motor, you have a voltage source, and there is a switch. So, with the help of this switch basically we try to supply the variable voltage basically, okay. So, this is the line voltage which is a constant which is available, and with the help of PWM, this is what the variable voltage we try to supply and try to control the motor. Now, this switch I just gave a mechanical example, but this switch could be an electronic switch consisting of a transistor and the diode, okay. And generally these DC motors are controlled by control signal emerging from the microprocessor, and in such cases we are going to we are using the pulse width modulation, okay. And the pulse width is modulated through the transistor which is switched on and off by means of signal applied to its base basically, that is over here, okay. And a diode is provided here which provides a path for current when the transistor is off and the motor is acting as a generator, okay. So, in that case it provides a path for the current when the transistor is off, okay. And this circuit can drive motor in one direction only, okay. And this is how we could have a faster that is in this pulse width modulation. If we have a large T over here, that is the voltage is there for a large portion of time. So, this is the faster one, and if the voltage is supplied for a small duration, this is going to be the slower one, okay. But as I was telling you, this circuit can drive motor in one direction only. So, what if you want to use the motor which can run in both the direction, okay. So, for that we need to use the H bridge circuit, okay. And this H bridge circuit basically looks something like this, of the shape of the H over here, as you can see, that is why it is called the H bridge circuit. So, there is a constant supply voltage here. There are 4 switches basically, you can see S1, S2, S3 and S4. Okay, so these are the mechanical switches. Actually, you have the electronic switches, and that switching is done with the help of transistor, say S1, S2, S3 and S4. Okay, so here motor rotates in one direction when switch S1 and S4 are closed and rotates in opposite direction when S2 and S3 are closed. Okay. So, basically that is in this direction one rotation when this and this closed, and in opposite one when the other two are closed. Okay. And as I said, in practice these switches actions are realized with the help of transistor and the diode. Okay. And for forward direction rotation, the potential A over here will be high and the potential B will be low, and for the reverse direction potential A will be low and potential B will be high. Okay. And here you see that, as I discussed in the previous slide, okay, the PWM signal is applied to the transistor base and that controls the switching. Now, let us see the speed control with feedback. Okay. And in case of feedback, suppose I am providing the feedback signal with the help of a tacho generator. Okay. So, suppose this is my motor, there is an output speed. Okay. I take out this output speed, give it to drive a tacho generator. Now, you see that this tacho generator basically gives you a voltage, that is we are getting the analog signal. So, I need to convert this analog signal to a digital signal, because this signal has to be sent to a microprocessor, and microprocessor cannot take an analog signal, it takes only digital signal. So, I supply this digital signal to the microprocessor, and then this signal has to be fed to the motor basically. Okay. So, and motor accepts the analog signal. So, we do a digital to analog conversion here, amplify that signal, and then we send it to the motor. Okay. And this is how the feedback signal is provided with the help of a tacho generator. Then we could also have the feedback signal provided by an encoder. Okay. So, in that case what is done is that the output speed of there is a connection of the output shaft with the encoder shaft. Okay. So, this encoder gives you the digital signal. Okay. And as I talked to you about encoder, we need to have a code converter over here. Okay, to convert the encoder codes, and this converted digital signal will be sent to the microprocessor. Okay. And then again rest of the things are same, that is we have the digital to analog converter, amplifier, and then this signal is given to the motor, and this drives your circuit. And if we have PWM used to control the average velocity for the armature. So, if we are using the PWM, then in that case what happens, you have the motor output shaft connected through the encoder shaft. Okay, here, and this digital signal with the help of code converter is converted again, the conversion of the code for the encoder rotation is done, and this is sent to the microprocessor, and from here we have the PWM circuit and the drive circuit. Okay. And this PWM circuit and drive circuit drive the motor, and that is how the PWM control of the motor is done. So, here are the references. If you want to read further, you can go through either through Bolton Mechatronics or our book on Intelligent Mechatronic Systems, or the Mechatronics Introduction to Mechatronics by Alciator and Histan. Thank you.